Next, we considered how alternative flowsheet structures can be defined, and here I have listed 7 main issues that we should be considering. Obviously, we can consider more things, but these are the main points that we should be considering in evaluation of alternative flowsheet structures. We will look at the detail of these issues in much more detail in chapter 5, okay, when we will discuss about flowsheet structures and recycles. But the main key point here is that there are several structures possible, and normally we have the help of heuristics to help us generate and assess these alternatives, okay? But ultimately, we need to do qualitative evaluation of flow sheet alternatives to be able to select between them. Okay, so the final decision always is based on the quantitative evaluation. Okay, and then that can help us decide if that is the best flow sheet or not. Okay, and this word best is defined loosely here. So please take a moment to have a look at information on this slide. So in section 1.4, I discuss here the technology selection as part of process synthesis. This slide highlights the key issues related with reaction technology selection and to separation technology selection. And you will be learning, or you might have already learned, most of the background material in other course units, especially, for example, considering catalytic reaction engineering and multi-component engineering separations. With respect to the reaction process, process synthesis requires us to select the reaction pathways, the reactor technology and its configuration, as well as the reaction operating conditions. And chapter 2 will address these design choices, and you will discover these choices with Dr. Venny. Process synthesis also requires us to select which separations will be carried out using technologies and which equipment configurations will be used. Okay, so we need to consider all these factors. We also need to select operating conditions for the separation processes, and we will look at these details in chapter 3 in detail. The next issue that relates to selecting the flowsheet structure is process integration. And firstly, and most familiarly, there is the heat integration. Okay, and here we consider how heat can be recovered within the process. Normally, we are thinking about heat rejected by a stream requiring cooling being taken up with the heat needing heating. Okay, or in simple way, we look at the process, part of the process that has surplus heat, and then we can actually use that surplus heat to provide to the part of the process that is in deficit of heat. You have learned about this in process integration course unit in year 2 with Simon and me. And when you were studying process integration, you were always given the stream data and try to find a way to maximize the heat recovery between streams in order to minimize the heat utility cost. In the context of process synthesis, because you are the designer or you are the creator, so we actually create stream data. And this gives us the opportunity to select units, their configurations, and their operating conditions in order to promote opportunities for heat recovery. Next, we consider energy recovery opportunities, that is the heat recovery and work recovery. Okay. For example, we can generate power when we expand and pressurized fluids, or we can generate steam via heat recovery and then use that steam to do work instead of importing power, for example, in steam turbines. Next, we considered process integration in terms of integration of material flows within the process. We need to take a system view in order to understand how recycle impact on the flow sheet performance. We should also consider how to recover, reuse, or upgrade material within the process that would otherwise be end up as waste. Okay, so sometimes you might want to recycle or further process your waste. Okay, or you might want to actually use a subsequent reaction system to further process your waste and then sell it to the sellers. And finally, we have opportunities to integrate process equipment as well, obtaining benefits in terms of capital expenditure or operating cost. One example is the complex distillation configuration introduced in multi-component separation unit that you will learn in this semester. Another example is the hybrid process, such as reactive distillation, where you combine the reaction and separation within one unit. Okay, and we will discuss that in a couple of examples as well. When we talk about heat integration of our process, we normally perform pinch analysis. And the pinch analysis provides us a methodology for identifying and evaluating heat recovery opportunities within a process. Okay, and you have seen that in year 2 in process integration unit. And normally you are given a set of stream data corresponding to the design and operating conditions, and you normally have a fixed flow sheet. Okay, and then you perform the heat integration of that fixed process. And the diagram here reminds you that the composite curves summarize the heat required by cold stream and the heat that needs to be rejected from the hot streams. Okay, so you want to make this balance so that you can recover all the heat within the process. The composite curves give information about the maximum energy recovery. Okay, the area that overlap between the two hot and cold streams is your energy recovery, and then you have information about your cold utility and hot utilities as well. During process synthesis, the designer, that would be you, selects a flow sheet structure and its operating conditions. And pinch analysis is useful for understanding the implication of these choices on heating and cooling requirements. So for example, if you decide to operate your distillation column at a different pressure than what was originally given, and how it is going to affect your temperature profile and how it is going to affect your energy recovery, you can evaluate that between two different designs by using composite curves. Okay, and let's have a look. Let's have a look at this example here. So the diagram on this slide suggests that you have a design 1 that is represented by this dashed lines. Okay, it gives you the energy recovery, its cooling requirements and heating requirements, and then you decide to change the temperature or operating conditions of this design, and then as such you have another design 2 that is given by these solid lines. Okay, and now you want to evaluate if the choices that you made are going to affect your process positively or negatively. Okay, so you can pause the video for a minute and try to think about if design 1 is better or design 2 is better based on this simple analysis of composite curves. So just looking at very simple analysis here, we can see that design 1 is more expensive in terms of its utility requirements, both in terms of its cooling requirement and its heating requirement. Okay, so without knowing anything more about these two processes, just by looking at its T&H diagram or composite curves, we can decide that if design 1 is more beneficial or design 2. So such improvements can sometimes be achieved by following the principle of keep hot streams hot and cold streams cold. I hope you remember that from process integration. And this principle means that you don't want to make choices that make your hot streams lose heat. For example, if your hot stream is hot, you don't want to expand them into a flash drum or through a valve so that they lose temperature. You want to avoid that. Although composite curves or energy targets give you an idea of the operational cost of your process, but all different designs still need to be evaluated considering the effect of process changes on your process yield, your energy cost, and your capital expenditure. Okay, so we need to still look into much more quantitative methods to evaluate your process. And chapter 4 will consider heat integration and also utility system in more detail. Process synthesis actively seeks to identify a range of options for achieving the design objective. For example, there may be different reaction pathways by which we can produce the desired product. For each of these pathways, there may be a range of technologies for carrying out the reaction and for separating the products of that reactor. For each of these resulting flow sheets, there may be a range of options for dealing with the byproducts and for dealing with the impurities. Okay, so there are too many options. As the diagram tries to show that the flow sheet options could be enormous. Okay, so our fear is that if we don't look carefully, we might miss the best opportunities. However, the best is defined. As I said, the best is very loosely and it depends on a range of factors in terms of its technicality and economic evaluations. But for now, we just say whatever the best is. On the other hand, the time required to fully assess each of these options could be hugely expensive as well. Okay, so we always have to make some choices. Now, to help us make these choices, we need a systematic approach to process synthesis to help us capture and not overlook the good process alternatives. And later in chapter 5, we will look at a structured series of questions supported by heuristics for this purpose. And heuristics are actually the industrial norms or the best practices that people have collected over the years that we can use to help improve our system or make our choice. But as I hope you will aware by now that there is no foolproof algorithm for process synthesis or there are no shortcuts, as I said in my first lecture. We have to still use the creativity and our engineering knowledge to make the best choice. Nevertheless, the optimization approaches can help to explore multiple options efficiently as well as the associated operating conditions. Okay, in chapter 7, you will look at this with Dr. Venny at some of the basic process optimizations and how we can use it for process synthesis. So this slide brings to our attention the concept of process control, and as designers or process engineers, we want to make sure that our process does not fluctuate far from our set values that we have used in the evaluation or in the design of our process or to evaluate between different flow sheets. As such, all processes require process control, and you will learn much more about process control and the different ways to control the process in the units of process control and process design in the coming semester. At this point, I simply want to note that the process control systems need to develop to control the process, okay? Considering both individual processing units and their impact on the whole process. Because in the end, you are designing a process, we are not designing a simple unit. We have to look at how individual units or the control of individual units are going to affect the overall process.